You're joining me now for the second lecture on climate change. We'll call this climate. We got a glitch right off the bat. Climate change number 2. Today's topic is the mechanism of the greenhouse effect. We could also think about this. So I'm gonna say this is mechanism. Now, climate change number 1 was just definition and observation. Here we're getting to the mechanism specifically of the greenhouse effect, and ultimately we're heading towards the concept of an energy imbalance that is produced by the greenhouse effect. Now, in order for us to get there, we need to do some drawings, imbalance, and we need to recall some stuff that you have learned in high school and maybe even elementary school. First thing we're going to get into is the atmosphere. So we have planet Earth, and above planet Earth we have the troposphere. I should do that as a dash line. And so this layer, 10 to 15 kilometers thick, that covers us as a thin veneer that allows us to live, is called the troposphere. This is where the greenhouse effect and this energy imbalance and humankind's influence is having a role. Above the troposphere is the stratosphere. The stratosphere is stratified. The stratosphere absolutely impacts climate and it impacts temperature, but it is not the big player. Stuff needs to be learned about in the future. Absolutely, that's the fact. But okay, and then the next layer above that is, we're just going to call it as near space. This contact between the troposphere and the stratosphere is called the tropopause, and it's about 10 to 15 kilometers above Earth's surface. Now, the composition of the troposphere, we could actually quiz you on it, but this is not a quiz, this is a lecture, so I'll just give it to you. 78% of the troposphere is nitrogen, and 21% of the air we breathe is oxygen, and 1% is argon. That sums to 99%, and these are the big components, and they are infrared transparent. I'm going to put infrared transparent. Now, when I say infrared, I'm talking about a wavelength of energy. The next thing we're actually going to get to is the electromagnetic spectrum. And I want you to remember what you can about the electromagnetic spectrum. But infrared transparent is what's important about those gases. That means they're transparent to heat. They do not absorb heat. Another way to say infrared and heat is long wave radiation. Now, the remaining less than 1% of our atmosphere is greenhouse gases, and some other things. But greenhouse gases like H2O, CO2, and methane, CH4, and these actually do absorb IR and produce the effect that we're talking about today, impacting the energy balance. Okay, now the electromagnetic spectrum. This is a range of different wavelengths, right? That's a symbol for wavelength of energy. The most famous wavelengths of energy are the ones we can see with our eyeballs, and they range between 400 to 700 nanometers in wavelength, and these are things like RGB. Blue, violet, reds, and oranges are on the longer scale. All right, and maybe you've seen a picture that's something like this to summarize. And here, so what I've done in this drawing is I'm showing the main energies produced by the sun are in this orange band, and the main energies emitted from the earth are in this red band. And so we can see here that some of the energy emitted from the sun is ultraviolet, some is visible, here shown with the RGB, and some of it's infrared. And then the energy that's emitted from the earth is infrared primarily. All right, that's what we're seeing here. So next up, let's talk about an energy balance. So we're going to start this with a picture of, and this again, this is almost an elementary picture. This is a picture of Earth and we have the sun up here, and the sun is emitting, okay, right? That's what the sun's emitting, these energies. And I'm gonna call those shortwave radiations. Shortwave radiations are coming down and they're hitting the Earth. Now, some of that energy strikes the Earth, and that's about 50% of the overall energy actually transmits through our atmosphere and it reaches Earth. Now, the other 50%, so I'm gonna say 50% reaches. 50% doesn't reach, and that 50% is broken up into a 30% that's reflected and scattered and 20% that's absorbed. How do we draw this schematically? Some of the energy comes down from the sun, bounces off of clouds, and gets scattered away. Okay, there's our cloud. We could have some come down and strike ice here on the North Pole, and it bounces away. And so this 30%, we're going to call it albedo. And albedo means scatter and reflection. These are produced by things like snow, ice, dust, clouds. Okay, here we go. Now, the 50% that does hit the Earth then gets transformed from shortwave into long wave energy, and it wants to escape, all right, or be emitted into outer space. So we could just call it like IR emission. But this escape is blocked by our greenhouse gases. We have CO2 and we have H2O and we have CH4 in the atmosphere. And so some of the long wave radiation that's trying to escape into outer space is blocked by those greenhouse gases naturally and stays within the atmospheric system. Now, by us humans changing the amount of CO2 or H2O or CO2 in the atmosphere, we could then increase the amount of this, or what could we say? We could impact the balance, right? Because we have input, and this is from sun, input from sun, and then we've got escape or emission from Earth. And I don't know if we should do a minus sign or a plus sign, right? But this is our balance. And so the science of this, or maybe it's the engineering of this, is we can change the energy balance by messing with inputs from the sun. Okay, that was an underline, not an equal sign. We could maybe increase the amount of ice, or we could increase the amount of clouds, or we could increase the amount of dust in the atmosphere and change the albedo effect, change the incoming part of these energy balance. Or we could change the amount of greenhouse gases in the atmosphere and therefore reduce the amount that's able to escape and change the energy balance. This is the greenhouse effect simply and schematically. Now I'd like to show you a figure that I've drawn that is going to, we're going to draw it here first. We're going to draw it here first because sometimes this is better for learning, for you to draw your own graph. And the y-axis is energy, and the x-axis here is going to be wavelength. And the sun emits, right? We're going to kind of do this exact same thing we just did above, but with a different kind of graph. So the sun produces this energy, and we could call this like ideal emission from the sun. But not all of that reaches the Earth's surface, right? Because of the albedo effect and because of absorption from the atmosphere, there's actually a lesser amount than ideal that reaches the Earth's surface. And that's this area in blue. And it would be the difference between those two, that delta, oops, I should change that color. We could go, okay, we go red. We go red. This area right here is that 50% that is either scattered or absorbed. We can think about okay, so this was sun. We can do this exact same graph now, but for Earth. The y-axis again is energy, and it's Earth's emission, and it's going to be wavelength. Now the wavelength here, I should put this down, is from 0 to 2 kind of microns. Because this is a shorter wavelength energy from the sun, maybe we could write that down, it's shorter. Whereas the emission from the Earth is longer. These are like, this is 5 microns to 50 to 70 microns. Microns. And so we could call this is long wave radiation. This is infrared. This is heat. And there's an ideal energy that we could put here. This is ideal. This is what Earth would like to put into outer space, but it is not what actually happens. Because of various gases, we actually only emit a spectra into outer space that looks something like this. And that's, I suppose, a little sloppy. But the delta between these two, this space, this is the greenhouse effect. This is energy that should be lost that isn't. And in fact, we actually even know that like water does the effect down here, and CO2 is doing this effect in this area. Here's water's effect. H2O is having an effect over here. Ozone, which is something I'm not going to talk about in this class, goes here. CH4 is here. So different gases absorb energy in different wavelengths, not allowing them to escape back, okay, to outer space. Actually, that turned out pretty good. Let's see what the actual figure was supposed to look like, just for kicks. All right, here's the figure that I drew to show for the in-class lecture. And you can see how we've got the same axes. This is the sun's emission, but less reaches the surface. Here's now Earth's side in blue. What would like to escape to space is what is emitted from Earth, but some of that's blocked. And it's these bits, how do we do this? It's these bits here, right? That are being absorbed by our greenhouse gases. Okay. So to wrap up, here's what I want you to think about. I want you to think about, what is the human influence? Right? For good or for ill? Maybe not for any emotional aspect of it, but just for positive or for negative, just in terms of quantity. So let's just like, how could we do this? The human influence can be in albedo. The human influence could be in greenhouse gases, right? We could do a lot of different things. Engineers, we could put more dust. In fact, we do more dust by farming. Or we could, this is kind of crazy, but we could actually make clouds these days. Maybe we do something with ice and snow. And by engineering, we could actually engineer an increased albedo effect that would, here's like the real energy that comes down from the sun. And by human influence, we could actually change it to be something less. And that would be producing like a colder Earth, an Earth with less energy. All right, we can play the same game now with greenhouse gases. And here what we're going to do is we're going to modify Earth's signature. All right, over here we were playing with sun's energy, but we could do Earth's energy. And so with our current understanding of the system, we know that Earth emits something like this into outer space as part of the background energy balance. But if we put in, what if we soaked up? What if we did less CO2, right? Miracle upon miracles, science and engineering combine, and we don't pollute our atmosphere anymore. Well, we would actually create a situation where there would be, we could say, more energy escapes. If more energy escapes, we might have a colder planet. That could be a runaway effect, and we could kill all of humanity. All right, I need to be careful with what I say. This is not like the current situation, though, right? The current situation is that we are probably going to put more CO2 into the atmosphere. If we put in more CO2 into the atmosphere, we're going to trap more energy. And so, okay, what is going on here? Then we're going to say less IR escapes to outer space, And if less IR escapes into outer space, then the energy balance is such that Earth warms. The net accumulation of this process is what we're concerned about right now. And I know we didn't get too technical now, but this is the idea of the greenhouse effect. Most of that energy, this is what we're having going on right now. It's an Earth warming pattern because we are producing more greenhouse. And that most of that energy gets stored in the Earth's oceans. So I'll leave you with one number, is that because of this imbalance, so we're going to say energy imbalance. There's an energy imbalance currently, and this energy imbalance, 90% of it is stored in oceans. And the reason for that is because the heat capacity of water is so much greater than that of atmosphere. But it's that 10% in the atmosphere that we're measuring in a lot of ways, and we're thinking about temperature because it's what we see every day when we look at our weather apps and check the news. All right, see you next time. We're going to get into the different greenhouse gases.